Hello, I'm Mr. Bob. Welcome to my Geometry Review video series. This video covers Chapter 11, Section 1, titled Tangent Lines. By the end of this video, you will have reviewed recent lessons describing tangent lines. Discussions will include using the radius-tangent relationship, finding angle measures, finding tangents, and reviewing a real-world problem requiring tangent knowledge. You will additionally review using multiple tangents, circles inscribed within triangles, and working with Theorem 11-1, which states two segments tangent to a circle from a point outside the circle are congruent. If you'd like me to cover any of these topics in greater detail, please leave your request in the comment section below. Please subscribe to the channel if you find this video to be helpful. Thank you. Okay, so let's start this video off with a couple definitions. A tangent to a circle. A tangent to a circle is a line in the plane of the circle that intersects the circle at exactly one point. The point of tangency is the point where a circle and a tangent intersect, and it is the point of tangency. Inscribed in. Previously, you learned that a circle is circumscribed about a triangle if all the vertices of the triangle lie on the circle. In that case, the triangle is inscribed in the circle. Circumscribed about. Similarly, when a circle is inscribed in a triangle, the triangle is circumscribed about the circle. Each side of the triangle is tangent to the circle. So I guess basically what they're saying here is when something is about it, it means it's outside. Circumscribed about means the thing you're looking at is inside what's circumscribing it. If it's inscribed in, it means that, in this case, a triangle might have a circle within it, right? So that's inscribed in. So I don't think that's too confusing, but I just wanted to make it clearer. Okay, objective 1, using the radius-tangent relationship. Earlier, you studied the tangent ratio in right triangles. The tangents you'll be reviewing here are related to circles. And so we have a diagram here. What they're showing is a circle, and point B is the point of tangency we were talking about before, that one point where the line actually touches the circle. And B is describing a segment or a line or a ray or whatever we're trying to attached to the circle at that point of tangency. So a tangent to a circle is a line in the plane of the circle that intersects the circle at exactly one point. That's point B. The line is that line AB. B is the point where it touches. The point where the circle and the tangent intersect is the point of tangency, right there at point B. AB, the ray, AB, is a tangent ray, and AB, the segment, is the tangent segment. So they define them separately if you have a tangent ray or a tangent segment. Theorem 11.1 relates to a tangent and a radius in a given circle. And as we see it here, it's the same picture we're just looking at. But it says, if a line is tangent to a circle, then the line is perpendicular to the radius drawn to the point of tangency. So if you draw a line from the radius of the circle, which is at 0.0 here, from the center of the circle, out to the circle's edge at the point of tangency, that is called the point of tangency, right? And it says here that line AB is perpendicular to OP. So AB is the line and OP is the radius attaching to that line at the point of tangency, and those two are perpendicular. So example 1, finding angle measures. So we have a diagram on the side here, and you see it's got this figure, the circle, and L, M, N, and O. Okay, so we're going to look about that. We're going to be looking for the degree of X. It's angle M. So it says in algebra, it says ML and MN are tangent to the circle 0. Okay. Find the value of X. Theorem 11.1, if a line is tangent to a circle, then the line is perpendicular to the radius drawn to the point of tangency. We spoke at that before. So O to L where line LM touches the circle, is a point of tangency, and OL, L is touching from this, is running from the center of the circle to the circle. That's forming a perpendicular line. And the same thing with ON and line MN. Those two are perpendicular because it's a radius attaching a tangent line at a point on the circle from the center of the circle. Therefore, given that ML and MN are tangent to the circle 0, angle L and angle N are right angles. L and N are right angles since they're perpendicular to each other. LMNO is a quadrilateral whose angle measures have a sum of 360 degrees. We know that from studying polygons. So, given that we know we have a total of 360 degrees, and we know that L and N are both 90-degree angles, and they tell us that angle LON is 117 degrees, we can do a little mathematics here, right? We can say angle L plus angle M plus angle N plus angle O, if you will, is 360. And we have, so by substitution, 90 plus X plus 117 plus 90 again is 360. Do a little simplifying, we get 297 plus X is equal to 360. And what's left is X equals 63 degrees. That's our answer, 63 degrees. Okay, example 1, check your understanding. Go ahead and stop the video and try this on your own. And when you come back, then you can continue the video and we'll work these together. So I'll wait. Okay, so I'm going to assume you've stopped the video and tried this. So let's take a look at it. So what does it say? It says that ED is tangent to circle O. Find the value in degrees of X. Well, from Theorem 11-1, we just talked about that a tangent and a radius connecting and the radius extending from the center of the circle out to the point of tangency forms a right angle. They're perpendicular. Well, if they're perpendicular, then the right angle's right here. Let's see, here's the right angle. Right here, ODE is the right angle. Then that means this is a right triangle, or it's any kind of triangle, but it's a right triangle. And that means that we have 180 degrees in the triangle, and they're already given us 90 and 38. So we can say that 180 degrees, we can say that, let's do it this way. Let's say that 90 plus 38 plus X is equal to 180. Okay? And X in degrees, right? In degrees. So 90 and 38, we're going to get 128 plus X is equal to 180. So now we're going to say X is equal to 180 minus 128, and the X is then going to be equal to 52 degrees. Okay? Okay, example 2, it's a real-world problem. So let's see what it says here. A dirt bike chain fits tightly around 2 gears. The chain and the gears form a figure like the one at the right here. Find the distance between the centers of the gears. So what do we know? We see the 2 gears. We see the front gear and the back gear. We see that the distance, the points of tangency is right here is 20. I'm going to see if I can. There's my pencil right here. Here it is. Is 26.5 inches. Okay. We see that the radius of the little circle here, the little gear, is 2.4 inches, and that the radius of the front gear, is 3.9 inches. Okay. And so what can we do to find out what the distance from here? They want to know the distance from here to here. That's what they want to know. Well, in order to do this, what we're going to do is we're probably going to draw a line parallel to this one right here, and I'm going to bring it down to the center of the small sprocket, and I'm going to take that parallel line, and oops, if I can do it, I'm going to go across. My lines aren't very good, are they? Anyways, so till I get to a point over here. And this is 2.4 inches, this distance from here to here. And I'm going to mark off 2.4 right here. So if you take 9.3 and subtract 2.4, we're going to be able to do something with it. So what does it say we're going to do with it? Well, A, B, C, E, there's a point right here. In fact, we can see it on the lower circle right here. Is a point that was added when our parallel line touched that radius. And it says that is a rectangle. And in triangle, AED is a right triangle because it's coming off of this perpendicular. This line is parallel to this line. This line here, the radius here, is perpendicular to the line that's 26.5 inches. So our new line is also perpendicular to this 9.3 inch radius. Okay? And it says here that the right triangle with AE, that's A is right here, the A to E is 26.5 inches, just like the BC is. So it also says that ED is equal to 9.3. That's ED right here. That's our line right here. ED is equal to 9.3 right here minus 2.4, and that gives us our 6.9 inches right over here. So now we have everything we need to solve this problem. So we're going to say that using Pythagorean, we're going to say AD, which is the distance between the centers of the gears, the sprockets, squared, is equal to AE squared plus ED squared, which is at 26.5 squared plus 6.9 squared. So that's the length of the new parallel line and our new segment over here squared, both of them squared and added. And when we do that, we're going to get AD squared is going to be 702.25 plus 47.61. Okay, and that's in inches. So the square of those two. Now we add them together, we get 749.86, and take the square root of both sides. When we do that, we get AD is approximately equal, because we took the square root of a number that wasn't a perfect square, so we don't really know what the real answer is here, so it's approximately 27.4 or 27.38, whatever we're going to go with, depending on how accurate you want to be. But we're going to say 27.4 inches. Okay? Okay, example 2a. Check your understanding. The direction says, a belt fits tightly around two circular pulleys, as shown at the right. Find the distance between the centers of the pulleys. So this is basically exactly the same as the previous slide with the bicycle chain. So what we're asking you to do is pause the video and try this on your own. And when you come back, we'll work it together. Okay, so now that you're back, let's take a look at what's I've got written down here and go through the steps. So a belt is tightly fit around two circular pulleys as shown at the right. The distance between the center of the pulleys, that's what we want to find. So we see that it's 35 inches between the points of tangency on the two circles. We know that those points of tangency and the line are perpendicular to the radius going from the center of the circle out to the point of tangency. And in both cases, on both of the circles. So this is information we already know. So we know that ABCE, it says, is a rectangle. Well, what is ABCE? Well, let's make it up here. I'm going to say that ABCE, A, B, C, and E is this point right here. And down here we have D. Okay, ABC E is a rectangle, and you can see I've drawn a line from here parallel to the line, the 35-inch line. I drew a parallel line down, starting then from the radius of the center of this small circle, and I carried it out until it touches the radius of the 14-inch radius circle. Well, that point there is I labeled as E. Well, that line is perpendicular to that radius, just like the 35-inch line on top is at C, because they're both parallel. Those two lines are parallel, and they're both parallel to the same line, which makes them both perpendicular. So now we know the distance from E to D. We're going to do that. We're going to add this right here, but E to D's distance is 14 minus 8. So you start with the full 14 inches, and you subtract the 8 we slid down. And now we come across, and there's 6 inches remaining. So ED is 6 inches. We have BC, or whatever, is 35 inches. So let's see what we have here. So we have AD is equal to AE squared plus ED squared. AE squared plus, yes, that's the little one. So it's AE squared right here. The line going across out from the radius to the perpendicular, attaching at E, and the 6 inches from E to D. So we have 35. AD squared is equal to 35 squared plus 6 squared. And when you add those up, you're going to get 1225 plus 36 after you square them. So that comes out to 1261. And AD is squared, so you have to take the square root of both sides, and we'll get AD is now equal to 35 and a half, so to speak. Could be 35. Yeah, we'll just keep it at 35 and a half, 35.51 if you wanted to be a little more accurate. But all we did is we took brought a parallel line down to the radius, struck it across, took the difference because we know that we moved it down 8 inches, so we can subtract 8 inches from this side. The rest is Pythagorean theorem history here. Okay? Okay, example 3, finding the tangent. It says here in Theorem 11-2, if a line in the plane of a circle is perpendicular to the radius at the end point on the circle, then the line is tangent to the circle. So AB, it says, line AB is tangent to circle's 0, or circle O. And you can see it. Here's the AB is the line they're talking about. Could be a segment, it could be a ray, anything you want you can make out of this, but they're saying that the line touches the circle at one point, at point P, and the radius extends from O to P, and the Theorem 11-2 says that this line is tangent. So AB is tangent to the circle at that point. So now we're going to look at the little diagram on the side. It says, is ML tangent to ON, or circle, not ON, circle N at L. So they're talking about right down here is ML, here's our circle line going from M to L. And they want to know right here, okay, here's where it's touching. They want to know, is it tangent? Is this line tangent? Okay. At L, and explain. So the explanation for that would be, we'll go back to the Pythagorean theorem, and we know that if a squared plus b squared equals c squared, then we have a right triangle. Okay. And we know what angle is the right angle, so it's the angle opposite the largest side in our case, right? So it's going to be angle L. So is angle L 90 degrees? Is this triangle a right triangle? So if you take 24 and 7, right? So what are we going to have? We have 24 squared plus 7 squared is 576 plus 49. You add them together, you get 625. You take the square root of 625, and you get 25. And since you get 25, and that is the same as what we have over here, this hypotenuse is 25, we have a right triangle. So L is perpendicular, ML is perpendicular at point L to NL. It says here, by the converse of the Pythagorean theorem, triangle MLN is a right triangle with right angle L. Therefore, line ML is perpendicular to NL, and ML is tangent to circle N at L. That's all due to Theorem 11.2. Okay, in example 3, check your understanding. They'd like you to go off and try this, so why don't you pause the video and try it yourself and see, is ML tangent to NL, or to a circle N, if you will, at point L? I'll wait for a couple seconds. Okay, I assume you've done that, so let's take a look at it. It says if NL is a 4, and LM is a 7, and ML is equal to 8, is ML tangent to the circle N at L? So again, I would say we're going to use the Pythagorean theorem. So we're going to say is 4 squared, let's do that, let's see, is 4 squared plus 7 squared equal to 8 squared? Well, let's work it out. 4 squared is 16 plus 49. Is that equal to 64? Well, 16 and 49 comes out to, looks like 65. So the answer is going to be no, it's not equal. And that's why we explain it, because this does not form a right triangle. The angles are different. It's kind of that simple. Okay, for objective 2, using multiple tangents. We're going to go over those definitions again. Previously, you learned that a circle is circumscribed about a triangle if all the vertices of the triangle lie on the circle. In that case, the triangle is inscribed in the circle. That's the difference between about and in, right? Circumscribed about, inscribed in or within. So, similarly, when a circle is inscribed in a triangle, as in the diagram right here to our right, that's the circle is inscribed inside the triangle. It's inscribed in the triangle. As in the diagram it says, the triangle is circumscribed about the triangle. About the circle, rather. So the triangle is circumscribed about the circle. This is hard to say. It's like a tongue twister. Each side of the triangle is tangent to the circle. So that's the key here, is that when you have this triangle like this, all these sides are all tangent. The circle's circumscribed within, or inscribed within, so that means that those are all tangent points where they touch. Okay, Theorem 11-3 will help you to solve problems about polygons and circumscribed circles. And we'll see probably that a lot in the future as we move forward. And what is Theorem 11-3? Two segments tangent to a circle from a point outside the circle are congruent. That's something they hadn't talked about that yet. Those segments, what they're saying here is, this is a point right here outside the circle. This point here and this point here are tangent points. We saw that in the definitions there. And it's also saying that this is congruent to here. That would mean that these are congruent. And that would mean, as we go around, that this one here and this one here. Oh, or did I miss it? This one here and this one here are congruent. A lot of lines being congruent there, but maybe I should clean some of them up. Let me clean them up a little bit. Let's get that cleared up there. The one I added that was extra, I think, was that one right there. So these are congruent. So let's go back to it. I jumped ahead and wrote my lines wrong. So this little teeny one, I missed it here. This one here and this one are going to be 3 dashes. I should have done it differently. But those two are congruent. So these two lines are congruent, these two are congruent, and these two are congruent. That's what that Theorem 11 says. Line AB, or segment AB, is congruent to segment CB. So, example 4, using Theorem 11-3, the diagram represents a chain drive system on a bicycle. Given or give a convincing argument that BC right here, let's see, BC, where's the pencil? BC is equal to GF. Well, so what is our argument? How do we know that they're equal? Well, let's see. It says here, extend BC and GF to intersect at point H. So what they want us to do is take BC and extend it out. So it's going to extend out somewhere. And they want GF, and they want us to take that and extend it out. And when they do, it's going to come intersect at some point H. Well, here's the diagram below. That's what they've talked about doing. So now they've extended them out. It's the same line extended out. Okay? So by Theorem 11-3, HC, H, the long line from H to C, is congruent to HF. We know that because the theorem tells us that. So those two lines are congruent. Or we could say, because that's what they just basically want to know, that BC, basically, if you know that, you're done. But they're also going to say here, or you think of it this way, HB, which is the small segment we just extended, HB, plus BC, the one that was already existing, is equal to HG, the one we extended on the other side, plus GF, the one that was already existing. Okay, so those are now equal. And by Theorem 11-3, again, HB is equal to HG, HB is equal to HG, because of 11-3. So by the subtraction property of equality, BC then, since these two long lines are equal, and we subtracted two equal lesser lines from them, the remaining pieces have to be equal. BC must equal GF. Example 4, check your understanding. So it says, give a convincing argument that BC equals GF, BC equals GF, if you know that BC and GF never intersect. They never intersect. So go ahead and take some time to think about that. And when you come back, we'll talk about it. Okay, assuming you've done that. So what does that mean? So we're going to look at BC. Right now, BC and GF intersect at point H. Well, in order for them not to intersect at point H, the lines would have to separate to where? The only two lines that don't, or lines that do not ever intersect are what? Lines that do not intersect are parallel lines. They never intersect. Well, if it's saying here that we know that BC and GF never intersect, then that means they're parallel. And if they're parallel and we know they're equal in size, then this must be a rectangle. What's going to happen is it's going to have two opposite parallel sides. It has to. Because that's the only way that BC and GF cannot intersect, is if they're parallel. So and of course, if it's a rectangle, then the opposite sides are equal, right? And that's the question here. Is BC equal to GF? Yes, it's equal because it's a rectangle. Okay, example 5, circles inscribed in polygons. It says here, circle O is inscribed in triangle ABC. Find the perimeter of triangle ABC. So you see here on the right, you see the circle inscribed in ABC, and AB, so that means that the circle touches these lines, line AB, AC, and BC, at points of tangency. And we know that points external to circles, to the tangencies, to the tangent points on the circle are congruent. So we're starting here. Let's see what it says. Points A, B, and C lie external to circle O, and AC, that's the long line, AC, AB, and BC are tangent to circle O, as circle O is inscribed in triangle ABC. That's the rule. That's our theorem here. So, by definition, the line segments extending from a point external to a circle and tangent to the circle are congruent. So if they're congruent, that means that AD, I'll draw it right here so we see it. I'm going to change the ink here. AD is congruent to AF, is equal to it. BD is equal to BE. BD, here's BD, is equal to BE. And finally, what is it? CE and CF. CF and CE, they are equal also. So, given that information, we now know that AF is equal to 10 centimeters. How do we know that? AF, it says AD is 10 centimeters. Well, we know that AF, we just said it, AF is equal to AD. So that means this is 10 centimeters. And if this is 8 centimeters, this one is 8 centimeters. And if this side, if BD is 15, then BE is 15 centimeters. So if we take our numbers, 8, 10, and 15, and add them together and multiply them by 2, AF is equal to 10, BE is 15, CE is 8. So the sum of all the segments is 2 times the quantity 10 plus 15 plus 8, which is equal to 2 times 33. 10 and 15 is 25, and 8 is 33, gives us 66 centimeters. Okay, example 5, check your understanding. This is your turn. Circle O is inscribed in PQR. So PQR has a perimeter of 88 centimeters. Find QY. Well, QY is this point right. I'm going to mark it here. QY is the point, is this line right here. That's what they want us to find, that length. So go ahead, try it. When you come back, we'll work it together. Okay, I'm assuming you've tried it, and I know you've all gotten it correct, but let's work on it. So, given all we know of the previous slides, we now know that, for instance, from point P, right here, to X, and point P to Z, we know that these lines are congruent and equal, because external points of tangency on a circle, that the lines are congruent. So that means that this is 15 centimeters. And we know that ZR or RZ is 17, so that means that RY is 17 centimeters. What we don't know is QX and QY. But we do know that we can add up 15 twice and get these pieces, and 17 twice and get these two pieces, and then what we're missing are these two pieces. Well, if we subtract 15 plus 15 plus 17, plus 17, that equals, what is that? That equals 30, 34, 64. Well, if we take from 88 and we subtract minus 64, we're going to get 24. Well, now we know that QX plus QY is equal to 24. Well, we just want QY, and we know that QX and QY are congruent and equal, so that means that we can divide the 24 in half. So that means that QY is equal to 12.